Hello engineers. Okay, so last class, I think Saturday, we discussed about the MOSFETs and the CMOS inverter. In our CMOS inverter, we discussed that how can we take it like when V input is increasing, how the output is that capacitor is charging or discharging, and how output responds with the different region from cutoff to that NMOS and PMOS, and how it will work. Okay, so now I am going for a tool. In the tool, we will discuss that how it will be response, and we will discuss about the static power dissipation and dynamic power dissipation, and we will also make a symbol also. Okay, so how that industry person work on it. So basically, we firstly design the circuit, and then we convert the schematic into a symbol, and then we test performance on the symbol, and we will check it. Okay, so let's start with that. Okay, that my screen is have a that is this is a library. You have here, it is library, that is analog circuit live. In the analog circuit live, we discussed last class is the NMOS car. Now I am going for new design, new cell, that is CMOS inverter, that is file and new, and go for cell view. In the cell view, I can write is CMOS inverter. Okay, and I press OK. If I press OK, so that we have a schematic window. Okay, in this schematic window, we can design a schematic or circuit. You can write it. Okay, so press I. We have a some that shortcut key, or you can go for create an instance like this, and you can press I directly. If you press I, that you have a add instance, just like an LT spice. You press that port, and you will find a lot of that you have a symbol, you can call it. Okay, so here I am using a GPDK45, that is a GPDK45. In the GPDK45s, we are using PMOS and MOS for making a CMOS inverter. In a CMOS inverter, we have a PMOS and NMOS, and we discussed that why we are taking as a pull-up network as a PMOS, why are we taking as a pull-down network as an NMOS, because PMOS is good for charging and NMOS is good for discharging. It will be good for passing logic 1, and it is will be NMOS is good for passing logic 0. So that's why. So we have a PMOS, and a PMOS we have a symbol. Okay, that here it is a description ki, okay, that length is what is the finger width, what is the total. We will discuss about the finger width and multiplier. Basically, every cell have a own width. Let that the starting width is that basic width or default width is 120 nano for a 45. But if you want more than that, let you are want 20 micro or 50 micro, so it may have a limit of 10 micro. It will not go beyond that. So by the help of fingering, you can increase the width. In terms of layout, you basically you that the width will be the poly will be connected in such a format, it will be a parallel. Okay, so if you want higher width, you can use a finger. Okay, just like this. Okay, let you have a this is 1 micro, let I am using a 1 micro, and I am using a 2 finger, so that the total width become a 2 micro. You can check it, the width become 2, the total width become 2, that finger width is 1 micro. So if you want as a multiple width, you can, okay, you can provide the finger width, and the number of fingers will be multiplied with that will be a total width. Okay, here that length is 45 nanometer. You can take it 45 or you can take it 500. Okay, it's up to you. I am going for 100 nano. Okay, so 100 nano my length and width. Okay, we will parametric analysis. We can change that width and length also as per the requirement, but I am just taking that. Okay, that this is your PMOS, where the PMOS have a width of 2 micro and length is 100 nano. Then I will go for NMOS. Okay, that is NMOS. In NMOS, you can, okay, we have a lot of NMOS. NMOS 1 volt, that will be a 4 terminal device, that is a 3 terminal device, that is HVT, that is high threshold. HVT high threshold 3, that high threshold means you have a that in terms of layer it will have a difference, that oxide become thick in if you are taking the layout. Okay, in terms of HVT as a circuit designer, you will find that higher threshold voltage. It is more stable. It will have a more power dissipation, but that speed is high. Okay, so that you can take is NMOS 1 volt. Okay, so it will be 100 nano. Okay, I am just taking that length is same and just put it that is 1 micro here, and I am taking that finger width is 1 only. Okay, okay, so this is your NMOS and this is PMOS. PMOS have a current towards the source, NMOS have a away current from the source. Okay, and you press W. For the W you can connect the wire just like this. That I am not dragging anything, I am just connecting, just like in LT spice you do, just connect it. Okay, the source is connected to body, the body is connected to source, so that VSB is 0, so that you will find that VTH is equal to VTH naught. Okay, and you have a input and you have a output like this. Okay, so till now we design a one, we are taking one PMOS from the instance, we taking the NMOS from the instance, and we connect source and body. Why? Because we don't want any VTH effect, that is body effect. Okay, so that body is connected to the source, VSB is 0 because VTH is equal to VTH naught plus phi under root 2 phi a plus VSB minus under root 2 phi a. So if VSB is 0, so VTH is equal to VTH naught. Okay, so I don't want any body effect, so just like this. Okay, and that connected, the gate is connected like this, and drain, this is source is connected to VDD, the source of the NMOS is connected to VSS, the output will be a that V out, and here it is V input. So for that we are providing the pin, that pin is P for pin, and I am providing input output for VDD and VSS. For supply I am providing that VDD and VSS. Okay, and for input I can provide the direction as a input is V in. Okay, V in. Okay, this is V in for you, and this is V out. Okay, this is your output. Okay, V out. Okay, just give the name and give the direction, and it will be like this. Okay, so this is your schematic of the CMOS inverter. You have VDD, you have VSS, you have input, you have output. If this that circuit is bulky, so I am using a label. But for now there is no any requirement of the label, so I am just using VDD, VSS, V in input, V output. So let's try to convert this schematic into a symbol, because we will use that symbol for the test. Okay, for the test batch. So firstly check and save, and go for create, and from cell view you can go for, from cell view you can generate, just fish again that you are going for create, for making a symbol, for create go to cell view, and from cell view you can design that symbol. Okay, that is the option is the CMOS inverter schematic converting to a symbol. Press OK, and that tool will define you. Okay, you want left pin as a V input, you want right pin as a V out, top pin as a VSS or VD, you can change that also. Okay, so I want that VDD at the top and the VSS at the bottom, left as I input and right as output. Just I am making like this. You can define at yourself. Okay, as per you, as per your understanding, as per your requirement, you can. Okay, so press OK. If you press OK, so you have a this type of window. You have that you have a V input, VDD, VSS, and V out. So this is a symbol that is a default symbol by the tool. Okay, you can change it. You just delete this. Okay, I am just deleting that key. Okay, I want uh, that symbol as per my requirement. Okay, so I can change that. So just I am deleting all these wires. I am not deleting this port. Okay, I am not going to that deleting this V input, VDD and V out and VSS. I am just connect that delete that outer boundary, and you can take the wire. Okay, you can take the wire. Okay, like this and like this. This is your that it will be become my inverter if you connect like this. Okay, and you can make like this. Oh no. Okay, so just check it. How can we provide this? Now it is okay. So you can. Okay. So this is your VDD. Press M for move. You can move it. Okay. There is no any requirement to touch that. Okay, that is just a symbol representation. There is no any requirement that this VDD or VSS will be touched out there. You can design as per your understanding. Okay, as per your requirement. Okay. So this is just a representation. Okay, so let I can move VSS to outer side. I can move VDD at outer side. Okay, and this will be connected like this. Okay, you can move V out as a outer side also. It's up to you. Okay, so this is VDD, this is VSS, this is input. Okay, if you want, you can make that outer side. So this is your V in, this is your VDD, this is your VSS, and this is your V out. This is your symbol. Now the schematic will convert into a symbol. You can simulate that symbol because in this symbol you have a schematic. Okay, we will check that. Firstly, check and save. This symbol is save. Okay, and you can cut it here. That there is no any requirement. If you go for that library, in the library you will check it that you have a CMOS inverter. In a CMOS inverter you have schematic and symbol also. The schematic is represented here and the symbol is looking like this. Okay, you can. Okay, so you have a CMOS inverter schematic and symbol. Now you can make a test bench that you can call this symbol because this symbol is helpful, or you can use this symbol for a simulation. So you can go for new and cell view. In this you can CMOS inverter underscore test. Okay, so you can go for test and press OK. So now you can call that symbol. Just you have a just like you call that NMOS and PMOS. You just go for that library that you have a, in which library analog circuit live. In this you have a CMOS inverter. In a CMOS inverter you have a symbol here. You can take that symbol for simulation. Okay. If you're looking at here, so this is your inverter. Okay, if you double click on this, that have a that schematic, you can check it. Okay, this is the schematic that will be present inside the symbol. If you press Ctrl E, you can back to that this symbol. If you double click on that, you can go for the schematic. Okay, now I am going for a simulation. So just press I. Okay, and I am providing that analog lib that is have a analog lib. You have analog lib, you have a sources, you have a VDD, you have a VSS, you have a voltage source. Lot of things are available in the analog lib. So for the source I am going for here, that is I am going for VDC. So you can check it here. So this is VDC you have, that is where it is. This is VDC. In this VDC you have a symbol and you can close it. Okay, and you can give any value. It's not meaning that I am just giving that 0.5 here, that is DC voltage. So you can connect it here, or you can make that outer side, that is you have a VDC on the input, you have a VDC for VDD, you have a VDC for VSS. Okay, so I am just giving that 3 supply for input, for VDD, for VSS. You can directly connect it also, or you can provide the ground also. It's up to you. Just I am giving that some idea. Okay, how can you? Because tool can understand as per you providing that label also. Okay, so just I am just giving that. Okay, so this is your that is net here. Okay, so I am just extending the net, and this is your output. So I want that one pin here. So for output I want that pin, that is V out. Okay, so this is your output pin. Okay, and now you can provide the VDD and VSS. So press L, this is for VDD and VDD. We have a two VDD for that labeling that this VDD is connected to this VDD. I am not connecting this wire, but basically by the labeling you can say that this VDD will be same as your this supply voltage, this voltage will be here. Okay, just like this you are providing L and you are providing VSS and VSS. This VSS here and this is also presented here. Okay, similarly I am providing V in. So this V in will be as a supply also, and if you connect it here, so this will be the input. Okay, so this will help you, that label will help you. Why? Because if you are using a routing, okay, that you are providing the VDD as a supply, you are providing the VSS as a supply, okay, and you are connecting the wire. Okay, so this circuit is very simple, so it is, there is no problem. But if you have a OTA, if you have a differential pair, if you have a current mirror, or you are designing a multiple current mirror or differential pair or voltage cascade amplifier or a BGR or anything, okay, the bulky circuit or ADCs, RADC and DAC, so that is lot of connectivity. Okay, so we basically prefer the label. Okay, so that will be help you. Okay, that there is no any requirement of lot of wire connection. Okay, and of course you required a ground, that you can go for GND. Okay, this is very simple there, just think in a such a way so you can. But of course before going to the tool you must have an analysis. Okay, this is happening here. Okay, you just, if you try directly on a tool, it is just like okay, you don't know anything but you just provide the supply, that tool will provide some output. Okay, if you give the input, tool will provide the output. But if you have an understanding of that, okay, that PMOS is charging, NMOS is discharging, this is happening here. Okay, how it will be increases, how it will be decreases, so it will be increase your information or increase your performance also. Okay, so just like this, so I am just giving that VDD. Okay, for 45 the nominal voltage is 1, so 1.1 or 1.2, so I am taking that 1 volt, that VDD is 1 volt. VSS, press Q for property change, you can provide that 0 volt, that is VSS is 0 volt, and that V input is any voltage. I am just sweeping the input voltage and try to find out output with respect of input. As per that input is changing, basically VGS. VGS means what? V input minus VSS. That V in minus VSS, that is your VGS, that VSS is 0. So basically V in is varying and you will find that what will be the output. Okay, so this is doing here, that go to launch, and I am going for ADE Explorer and go for the create new. In a create new I am press OK, and this is providing a Maestro window. In the Maestro window you have this type of window. Which type of simulation you want, just go for the create here, and I am going for DC simulation. Okay, last class we discussed we have a different type of analysis: transient, DC, AC, noise, stability. Okay, so transient will help you to define the delay, rise time, fall time, means everything will be related with the time that will be simulate on the transient response. Transient analysis, if you are interested for the power static, means DC, means that DC operating point, DC analysis, static power, that will be related to the DC analysis. If you are interested in terms of frequency, that you will go for the AC analysis. So these are the basic analysis, the transient, DC and AC. So here I am just sweeping that DC voltage, the input voltage, and try to find out what will be the effect on the output side. So just I am sweeping the DC save DC operating point, and I am sweeping the DC voltage. So I sweep that component. Okay, so let's go for the component and select component here, that I am sweeping this component voltage and DC voltage. You can sweep lot of things, that you can sweep DC, you can magnitude, sweep the magnitude, you can sweep the phase. That will be requirement as per that you are going for AC response. But now you are going to sweep the DC only. So I am sweeping the DC voltage. Press OK, and you can where that maestro is here. Okay, oh sorry, this is not maestro. The maestro is here. That is okay. You have a that analysis. In this analysis, that you have a V2, you can directly write the V2, or you can just click on that. So V2, and press, you are moving the sweep from 0 to 1 volt. You are basically sweeping the input voltage from 0 to 1 volt, 0 to VDD, or 0 to 1 volt. And this will be automatic. The sweep can be automatic. You can provide the linear also. The step size, it will be 0.01, because that will be, this is 0, then 0.01, then 0.02, then 0.03. On the basis of that, you will find that 100 steps, and from 0 to 1. Okay, and press OK. So these are the DC analysis. And you want the output, go for output. To be saved, select on design. You want output with respect of input, you can. Okay, and you can go for simulation. Okay, so just I am that you have. Okay, just go for plot also, just click on the plot. So you can see it. Okay, so that will be a plot. You can run, and after that net listing or simulation will done, that output will be response, that how the output will be generation. Okay, so this is the output, that V out is changing. This is your V out, and this is your input, that V out and V input is here. Okay, you can change that width also, that is extra width. Okay, so you can check it, that V out is flowing from the higher to lower, that V input is like this. And if you are looking this point, so this is your the point at which the V out is crossing the V input, or V input is crossing the V out, and you can find it. Okay, so this is the voltage, is that what you can just press mask here, and you can check it. Okay, or you can press V for vertical, and you will find it. Okay, 523 millivolt will be a 524 millivolt. Okay, basically you are providing 0 to 5 volt, 0 to 1 volt, so that center point will be a 5. Okay, 0.5. Okay, but now it is showing that 524, means that 524 voltage is on the leftmost side, and rightmost side, that 1 minus 524. Okay, that will be, I think, 476. Okay, that 476 millivolt. Okay, if I am not using 0.45. Okay, so this is the way you can shift that width. Okay, you can and change that output response toward the left side, on the right side, on the basis of the parameter variation. So let's how it will be work. Just go for that. Okay, I am just going for a circuit. Okay, sir, there is circuit. So just going for a circuit. Okay, you have a CMOS inverter. In this CMOS inverter, I want to change something. Okay, just double click on this, and you have a schematic. In this schematic, if you want, you can change the width of PMOS or NMOS. It's up to you. I am changing the PMOS width. That press here, that is like what that is Q. Okay, and I am giving that finger is that name is X. That is, X is a variable. Okay, so if this is X, so that this is a variable, and you can change that width of that finger width. Okay, so I am just putting that X is variable finger width. Press OK. So that total width become a 2 times of X, because that number of finger is 2, and the finger width is X. Okay, so this is the way. Okay, just an okay, and control E. If you press control E, So you can back on that. Okay, just press maestro here. Okay, so I am taking one variable, go for the design variable, and you can put it, what was the variable, that x, and you provide that any value. Let I am providing that 1 micro. Okay, so this is the way that you have 1 micro. You can increase that value also 1 micro, or you can make it 0.5 micro, from that to 0.5 micro, 1 micro, 2 micro, 4 micro, or 3 micro. It's up to you. Means you can 4 micro, 5 micro. It's up to you. Okay, so you are providing that different width of the fingers. Okay, on the basis of that, that response will be happen, because you are changing the width. Okay, so now the output response will provide the different output with respect of input. The input is same, that it is increasing from 0 to 1. There is no any changes of the width, but the output is changes because that the width of the PMOS is changing. So I am just putting it here, that different value of x, that PMOS width is increases, that it increases from 0.5 to 5, 0.5, 1, 2, 3, 4, 5. Okay, and just run it. If you just run it, it will provide that, okay, what will happen with the different width, that 0.5 or 1 micro. It is showing that parameter x 500 nanometer, 1 micro, 2 micro, 3 micro, 4 micro, 5 micro. That will be V out and V input. V out will not change because V out is not, and that V input is not changed because V input is not dependent on the width. Okay, so V input is not changing. V input is just sweeping from 0 to 1. V out is changing. Okay, so basically V out is changing. You can check it here. So that V out, you can check it here, that V out at 500 nano, this will be this, as per the width is increases, it will be shifted towards right side. In a CMOS inverter class, we discussed that as per the width will increases of PMOS, it will be shifted towards right side. If NMOS width will increases, shifted towards left side. Why? Because that width will increases means the resistance will decreases. V out have that V out will be more towards that VDD, and it will be that V input required a higher voltage to make that ground, okay, towards that 0. So that is V out is that for 1 micro it is like this. For V out 2 for the width is 2 micro, it is shifted towards right side. So basically what is happening, the threshold voltage of the MOSFET is increases, it is shifting towards the right side. So basically you can check it that at the 4 micro, at the 5 micro, as per that the width of the PMOS is increases, it is shifted towards the right side. Okay, okay, so if you want, I can increase that thickness of that, so that you can better understand. Okay, shift and width on that and go for the extra thick. Okay, so it will be like this. Okay, so this is happening here, that what will be that response, you can press V. Okay, and you can check it. Okay, so this is happening. Okay, so you can check it. Okay, so this is the value, that what is that value, you can, okay, you can want only if you want only that V out, so you can, go for this. Okay, so it is visible all. Okay, there is no any requirement of that. Okay, so at the point of this you can check it. Okay, if you want, you can want it like 0.5. It is 0.5. At 0.5, or make it, you can change it here. Okay, you can change directly here, that is 500 millivolt. Basically you want 500 millivolt, the output will be 500. But now this is at 500 millivolt, that output will be that at the range of the input of the 500, the output is 669, 935, 975, 984, 988, 995. Because that as per 500 millivolt, the output is very high. You want to decrease the output towards the left side, the output is shifting towards right side. So you can reduce the width of the PMOS from 0 point means it is less than 0.5 micro. Okay, because if you are going for higher width, it is showing that higher voltage on the V outside. So you want find from 500 nano. At 500 nano the voltage is 669. You want V out and V input at the same voltage, means at 0.5 of the input voltage it will be that 0.5. You are trying, okay, it may be possible, it may not be possible, because that will be a lot of effect here. So I am just trying, okay, let make it closer that, okay, let list small that here, okay, just make it not, this is not required, okay, make it 0 0.1 micro, 0.2 micro, 0.3 micro, 0.4 micro, and 0.5 micro. So that we have a different x now. Now it will be a 0.1, that is finger width, and now it will be what, that two times of that. So 0.2, 0.4, 0.6, 0.8, and 1 micro. Okay, so let's try this. Okay, so just I am running that on the different width, and now the width of the PMOS is lower as compared to uh, previous one. So okay, there is a simulation error. Why that be a simulation error? Okay, so now it will be here. That is 200 nano. Oh, sorry, that is 200. That is 300 at 400 and 500. You can check it. Okay, what will be the output here? Just press V here, and you can check it. You can provide that. Okay, the voltage is 500. So just provide that 500 millivolt. At 500 millivolt, what will be the output? At the 500 millivolt, the range is 537 at that 400 nano, and 300 nano it will be 377. So 377 and 537, in between that you have output at 500. So let's make it 350 to 400, and 350 or 300 to 400, you will find it, okay, that the output will be near about 500. Okay, so you can, basically I am using iteration method. I am not going for a GM over ID method. I am just giving the basic idea what will be happen. So just I am giving 0.3 micro, 0.5 micro, sorry, 0.35 micro, and 0.4 micro. Okay, let provide that this is three values at 0.3 micro, at 0.35 micro, and 0.4 micro. Just run it here. Okay, so now the width is 0.3 micro, means the PMOS width is 0.6, 0.7, and 0.8 micro. Okay, so let's figure out what will be the response. Okay, so that is the way. Okay, so now the output response is like this. You can change that the width of that, because it will be easy to uh, show you that extra thick. Okay, now you can provide V here, V for vertical, and I am providing that the width is 500. Okay, so just I am changing the value. Okay, make it, okay, just 500 millivolt. At 500 millivolt, what will be the value? That value is 377, 460, and 537. Means at 350 millivolt, it is 350 nano, that will be a 460 millivolt. At 400 nano, means at 400 nano of X, that will be a 537. Basically, this is 350, that will be a 700, and that will be a 800, because the width is, total width is two times of X. So as per that, you can set that, okay, this will be okay or not, this will be okay or not. Okay, you can. Okay, so from that value to this value, as per the iteration, you can set it. Okay, so if this is near about 500, so that will be provide the less delay also. That will be a rise timer fault time. Basically the input is changing from 0 to 5, the output is changing that 0.5 to 1, or that if the input is 0.0 to 0.5, the output is high. If you are changing the input from 0.5 to 1, the output is low. Okay, so you can provide as per the iteration, you can. Okay, similarly, you can plot the current also. If you plot the current, you basically look at here. The current is always be in that point, that this will be a different region, this will be a different region. As you know that in a steady state, that current is zero, because that one of that MOSFET is off. It may be PMOS, it may be NMOS, and then a steady state, it will be providing that change at that 0 to 1. So that's why I am sweeping the input. Okay, and you can check it that output uh, at the current also. You go and go for output and go for the select on design, and you can go for that current also. Okay, that VDD. Okay, and you can check it. So now that what will happen, let's check, let's figure out. So this is pending here. Okay, that it is doing that output is change, that output will be performed. Okay, so now it is not showing. Okay, that output is not showing here. Let's try to go for schematic. Okay, it is not showing here, so you can go for that schematic. So you can go for output, press here and go for schematic. In this schematic you can check like this. Okay, go for maestro and you can go for output to be saved, select on design. Now you can check it, the output is like this. At the source side or the drain side you can take. Okay, it's up to you. You can remove that this is your I not VDD. Okay, you can delete it. Okay, basically this is not required. Okay, so this is I out VDD. Basically I want the current at that this point or this point. Okay, it's up to you. Okay, and just check and save and run it. Okay, so you can, so it is calibrating that value and run it here. So why this is not showing that output of the current? Okay, just check it why this is not showing that. Okay, so let's figure out why it is not showing. Okay, is there any problem? Okay, why it is not showing that output? Select on design, that current here, and it must be showing here that output current, but why it is not showing? Okay, let's figure out. It may be showing some error. No, it is not. Okay, just go for another maestro. It may be we have a problem. Just go for next maestro. ADE Explorer, create new, just go for OK. Just I am pressing OK. Yes, I want to overwrite. Okay, just I am going for DC analysis. Go for here, component parameter. You can select the component from the schematic, Control E, and this is your component. You can press on that VDC. Okay, and you can, that you have a V2 here from 0 to 1. Okay, and you can go for linear. Here you can provide that step size is 0.01 or automatic, it's up to you. Press OK. You can provide the design variable is X. Of course that was X, and let I am providing this 0.35 or 0.35, it is 35 micro. Press OK. Okay, and I want the output, that is I want the output from this to be selected on design. Okay, So okay, it will be showing like all these things. No, I don't want this. Okay, I don't want these plot like this, like this. I don't want this. I want that V out and V input. So just go for CMOS inverter, and I am just clicking on that, and go for schematic and go for Maestro. I am going for output to be saved. Select on design. I want that output, input, and I want current. Okay. Now I am just checking that everything is okay, that you have output, you have input, you have a, and I think now it will be showing that current. Okay, so it will taking some time. Net listing is doing now. Oh, now this is have a current. Okay, great. So you have a output, you have a input, and now you have a current. So basically I want to represent here basically that V out is that MOSFET in saturation region, that MOSFET in saturation region at this part, when the V out is crossing the V input, at this point only you will find the maximum current. In terms of steady state, the current is 0. If current is 0 or that current is picoampere, that is very small current, picoampere into voltage, that VDD, that VDD is 1 volt and this current is picoampere, that is that volt power is picowatt. Okay, so the current at the steady state is 0, but once you are transient in this response from 0 to 1, if your that input is changing from 0 to 1, the maximum power will be dissipate at that when V out is crossing the V input, where that both MOSFET in saturation region. This is the region where the both MOSFET in saturation region, and the current is 4.4 micro. That will be 4.4 micro into 1 volt, that is VDD. So it will be 4.4 microwatt. Okay, that will be a too much amount of, or you can 4.4 into that amount of voltage, that is 500, let 500. So it will be 2.2 microwatt. It is like this. Okay, so this is the way, okay, that you can understand the maximum power is only possible when both MOSFET in saturation. And if you are in steady state, that's why in a digital design we always talk about that in a steady state means that logic 0 or logic 1, the output, the power dissipation is only happen at 0 to 1. If you are transient response 0 to 1, then only you can. Okay, we will check that at the transient analysis, but this is the way. Okay, so this is that value, and you can go for you can check that power also of the DC analysis. You can go for that output, save all. In the output and save all, you can save that power all. If you save the power all, you can, if you run it, that you will find that okay, this is running, and that of course cadence required a command. If you provide that okay, I want a power, so then only you can go for output and save all, and you can go for browser. Here you can check it, that is the power here, and this is the power. Okay, so you can check that the power is like this, that just like I in, that is power. Okay, basically power is like this. Okay, this is uh, this is the power. Okay, that is 4.4 microwatt. Okay, so this is the way. So that the way that power is only dissipate in the terms of that at this time only that. Okay, so this is the way you can understand the power and something like this. So power is only, maximum power is only happen at the at when that V out is crossing the V input, that point at which the both MOSFET in saturation region. Okay, let's talk about that transient analysis. If you want transient analysis, you just simulate that circuit in terms of transient. Okay, now I am going for the transient. So just change the input. Okay, the input is here, that control E, and now the input is not VDC, I am providing the V pulse. So press Q, and I am going that here it is not a VDC, it will be a V pulse here, that is V pulse. I am providing that V pulse here, and I am providing that 0 DC volt because there is no any voltage here. So the voltage is 0 here. So DC volt is 0. I am just providing the input voltage, the input response, that voltage is 0 to 1, 0 to 1. Okay. So 0 to 1, what will be the period? I am providing that, let that period is 1 microsecond, that whole cycle is completed in 1 microsecond, and the pulse width is 0.5 microsecond. Okay, you can provide that the delay. Okay, I don't want any delay, that starting time. Okay, rise time of all time, you can provide a 10 picosecond or 10 picosecond, that is too much, 10 picosecond and 10 picosecond at rise time and the fall time. And that from 0 to 1 it is happening in 1 microsecond. 0 to 1, 1 to 0, that is 1 microsecond. The 500 nanosecond from make it 0, and then it will be make it 1. And the rise time and fall time is 10 picosecond. Press OK. Okay, now the input will be your pulse. After changing that, just please go for that check and save, because without check and save you don't you will find that the error or warning. Okay, now I am going for transient analysis. Just go for transient, not for DC. Let I am going for 5 micro. It will be a 5 micro. That 5 micro, that will be enough for that. Okay, I want the output response, that for my 5 micro means the cycle will be 5, 0 to 1, 1 to 0, 0 to 1, 1 to 0, and at x is equal to 0.35 you want V out, V input, and the current. If you want current, that is okay. If you don't want, you can understand like that. Okay, just run it, just run it. Okay, so if you run it here, that it is providing the net listing, it is taking some time, and it will be like this. Your I am just scatter that response, and you find that V input is 0 to 1 to 0 like this, and your output is changing from like this to this to this to this to this like this. The output is, when the input is high, the output is low. When the input is low, then output is high. Okay, and when input is high, then output is low. And you can check it, the current is only possible at the transient state. It is not showing the steady state. When the input is 0 perfectly or input is 1 perfectly, that power, that current is 0. Current is nearly about picoampere current. But once that transient is happened, why this is just looking of that, okay, this is basically what is happening. The input is changing here from 0 to 1, the output, that is like this. Okay, so if you are changing that 0 to 1, that the power is like this. Okay, so you can, okay, and that you can change that waveform. Okay, that output is not as much good as you want, that output is not perfectly, it is showing some spikes. So you can change the width and length, and you can. Okay, so how can I? So I am just giving some. Okay, so I am just want to change that circuit. Okay, just make that okay, just make that width is uh, that make that width is, I am making that width is 1 micro. Okay, and just run it. Okay, I'm just giving that value. Okay, x is equal to 1 micro, and run it. Okay, now check it, that the output response, you can check it, that okay, what will happen. So your output is showing some edges on the why this is happening, because it is showing that high current is happening for the discharging. The capacitor is charging or discharging at this time, it will be high enough so that it will be showing spikes. Okay, you can reduce the spikes as per that W by L. Okay, as per you are providing the W by L, you can set that, okay, this you can reduce that spikes. Okay, so that current you can reduce so that that capacitor will not, or you can provide that input that rise time or fall time is 10 picosecond, make it higher so that it can be, because that in a 10 picosecond only it is changing. Okay, so let's try that what is happening. So just go for that, and here that at 10 picosecond it is happening, make it 10 nanosecond, that you give that enough time for 0 to 1 and 0 to 1 to 0. So the rise time is and fall time is 0 to 1 is 10 nanosecond and 10 nanosecond. So as per that time will reduce, as that current will be also that I is equal to C dV by dt, V is equal to 1 upon C integration of I dt. So if dt is small, so current is very high. If dt is some large, so the current will be lower. Okay, so just check it. So now what will happen? So I am just changing that the rise time or fall time, and now you can check that what will happen. Okay, that is the great. Okay, so you can. Okay, so if that rise time and fall time is 10 nanosecond, so you are giving the enough time for charging and discharging. So basically I is equal to C dV by dt, and dt was very small, so that because 0 to 1 and 1 to 0 in a picosecond, so that's why it will be showing that current will be very large, and that will be showing in your output response. That is the practical way. So you just change that. Okay, or you can change the width or length as per that. You must trade off in between width and length and something like this. Okay, so this is happening here. You can check that delay also. You can go for check that, right click on this, send to calculator, send to calculator, and you will find that you have a delay option. In that delay you can check it. Okay, so you have a V input, and you can go for, you have a V input here, you have a V out here, you have a V out, you can go for V out also, control X and go for control V. You have an input, you have an output. The threshold voltage is 0.5, basically 0 to 1, the propagation delay is 50% of that. So 0 to 5, 0 to 1, that is 0.5 will be the propagation delay. 0 to 1, that edge number is 1 and 1, and check it is falling or rising. Just check it that the input is rising. I think input is rising from 0 to 1, and output is falling from 1 to 0. So input is rising, output is falling. Okay, so you can put it that as number 1 input, that signal 1 is rising, and the h, this is type 2, that is output is falling, and everything is same. Press apply, you will find that. If you click on that, you will find that delay. Okay, so you have a delay of 344.9 picosecond, or you can press apply, and you can go for that window right here. So that will be a ADE. You can go for Maestro here. In the Maestro you will check that ki, okay, you have output setup. In the output setup you will find that you can provide the name also. The name is delay. Okay, and that was delay for what? For 0 to 1, when the input is rising from 0 to 1. Okay, so it will show that value. Okay, that will be like this. Okay, so similarly you can go for 1 to 0. So some same input, same everything is same, just change that ki, okay, that this is falling and this is rising. Okay, and you can plus apply here, and now you will find that delay is 178. Why? Because you have a change of x. Okay, as per the change of x, the rises time is different and falling time is different. And why it is showing minus? The output is fastly, that output is become a zero point 0.5 fastly as compared the V input. So that's why this is x minus y only. The delay is just minus x minus y. There is no any requirement. There is no any difference of minus. Okay, that this is just like 1 minus 2 or 2 minus 1. Okay, so this is the way. Just press apply. Okay, and you can click on this and you can provide here. So where it was, where that will be here. So you can check it. The delay is this value is what delay, uh, that will be 120. The input is 120. Okay, 120. Sorry, 120. Okay, so that is the way. Yes. Okay, you can put that width was, make it 0.35 if you want, 0.35 micro. Okay, or something like this, and you can check it. Okay, 0.5 micro, 0. Let put it 0.35 micro. What will be that delay? Okay, so just put it and run, and let check it. What will be the output? So this is happening. Okay, so the output is like this, and now check that what will be your delay. Okay, so you can check it. This is 92 picosecond on 27 picosecond. That delay for 0 to 1 is higher. That input is rising. 0 to 1 it is taking 92 picosecond, but 1 to 0 it is taking less delay, that is 27. So there is a difference of that. Why? Because that W by L is not perfectly matched. It will be if it is perfectly 500 millivolt at a 500 millivolt, or you can provide it such a way you can reduce that the delay also. Okay, you can check that power dissipation also, the dynamic power dissipation. So you can go for classic and browser. In the browser you can check that dynamic power, the transient output. uh, Transient, here you will find that power will be like this. So this is your power. Okay, so that power you can make it bottom side. Okay, so this is your power, and that power is what? That is dynamic power. You can provide the average always. Dynamic power in terms of delay, send to calculator, and you can go for average value. You can go for all function, and you have an average here, that is average value. So this is average of that. Okay, so you can check it. This is 14.57 nanowatt. Just apply it here. That will be a function. Just click on this, and you can go for here. This is showing your what, your where it goes. It is not here. Output setup is like here. That is dynamic power. So this is your dynamic power. Okay, so as per, okay, so you can check it. That is, you have a dynamic power, you have a delay, you can check out the rise time, fall time. Okay, you can. Okay, you can change that x, and you can find that delay. Okay, what will be happening here, what will be do. Okay, it's up to you. Okay, so you can, if you providing 0.35, what will be happen? If you providing 0.4, what will happen? So you make a table of that, and you can. Is it okay? So this is the way, and you can run it. Okay, on that, there is no any requirement of the output. Don't require the output. I just check that, okay, what is happening on the basis of the different value of x. You can check it. Okay, if you want, you can. Okay, just 0.35, 0.4 micro, 0.5 micro. Okay, on different value of that, you can check it. Okay, so on the basis of the different value, you can. what will be your output. Okay, what will be the delay on the different bits. Okay, so you can, okay, so this is the way you can simulate the tool. Okay, and you can perform that response and analyze. Okay, so everything you can. Okay, but firstly you must know, okay, what is happening, or what is the way you can toggle that. Okay, so you can check it, that if you are taking the 350, it is 9227. If it is 125, if you are taking that 400 nano, it is 125. If you are taking 500, and that is 182 picosecond. So that is the way. That means you can go for 0.25, 0.3, okay, and you can go for 0.35. That is the way you can. Okay, so this is the way you can. Okay, so for 0.25 micro, 0.3, 0.35 micro, what will be the power or delay or everything you can calculate it. Okay, so you can make the table also, and you can make that table like this. You can represent your output in your project or your thesis or your anything. Okay, so these are the requirements. Okay, so I am just taking that. Okay, this is 19.2 picosecond, 0 to 1, this is 20, this is 57, this is this, and that 165, 90 to 27. So you can make it trade off. Okay, which one is better, what is the requirement, what is the design specific requirement of the rise delay or a fall delay, and on the basis of that you have a power dissipation, that 11.48 nanowatt, 11.48 nanowatt, and 14.57 nanowatt you can. Okay, so I hope it is enough for today. So that is, you just know, okay, how can we simulate, how can we make the symbol, how can we this simulate of the CMOS inverter. Okay, you can take that as a homework. Okay, just put it resistance here, just put it resistance here, or just put it resistance here, just make a one circuit where that you have a resistance with a PMOS, in a second circuit you have a resistance with a NMOS. What will be the output response if you are taking 0 to 1 or 1 to 0? Don't go with that just response, just think in a way, okay, that if you are putting resistance here or resistance here, the output will be, what will be the effect on the output side. Okay, so this may be your assignment, please work on it, then only you can understand, and this question will be help you to analyze what will be the effect if you are increasing that resistance or you are attached that one resistance, CMOS inverter, that is okay. Okay, and the second assignment is that let I am replacing the PMOS with the NMOS or NMOS with the PMOS, what will be your output? Just sweep the input 0 to 1 and check it. If this is NMOS and if it is PMOS, what will be your output? So you have a two assignment. The first assignment, you can put one resistance with the PMOS and one resistance with the NMOS in A part and B part and check it. In the second question, just find it, okay, if you replace PMOS with the NMOS or NMOS with the PMOS, what will be the power? What will be the output response when the input is rising from 0 to 1? Okay. So I think it is enough for today. Let's stop it here. Thank you so much, everyone. Bye bye. Take care, dear.